Okay, good morning everyone. I am Enes Veliu and I am from Albania, quite a seismic-prone country. So, in my PhD dissertation that I was supervised by Dr. Vitor Silva, we addressed the advanced earthquake modeling of human losses. And first of all, why is it important to study human losses? According to MDAT 2022, nearly 10% of the natural disaster fatalities are caused by earthquakes. So nearly 2.3 million out of 23 millions are dedicated to earthquakes. Coburn et al. 92 found that 70% of earthquake-related fatalities in the last centuries were due to building collapses, and this figure can go up to 90% if no follow-on events such as fire following, landslides, or tsunamis take place. And why is important? I mean, in long-term real-time fatality estimation are crucial for effective risk-informed decision, emergency preparedness, insurance and reinsurance industry, urban planning, rescue and search operation, and emergency management. Earthquake-related deaths tolls arise mainly from three causes, but not only from three, but mainly. So the first cause is non-structural components, structural component, non-structural components, and follow-on events such as tsunami, rock falling, landslides, and fire followings. Let me introduce you to the current state of the practice in fatality modeling, and I'm starting with a famous paper of Coburn et al. 92, where the estimated number of fatalities depends on the probability of collapsed building and the number of collapsed buildings, the number of occupants at the time of earthquakes, and the number of people that are trapped inside the building in the moment that the building collapses. And this parameter is really important because it is related to the building volume reduction. So yes, for example, if you see the picture below, for economic losses purposes, the building is done, is classified in damage state 5, so the loss ratio can be 1 or a bit more than 1. But when it comes to fatality estimation, going from left to right, we see that volume reduction changes dramatically from 10% to 100%. So the same trends trapped people will follow. And then it is the parameter M4 and M5 that consider the number of people that die immediately or the people that are injured but they die afterwards. So similar work is conducted by Spencer in 2017, and he proposed like 12 archetype building based on the past event including Northridge earthquake, Kobe, Athens earthquake. So he proposed fatality ratios. And in 2013 it was Soap and Spencer again that proposed the empirical fatality rates, completely empirical, based on a database that contains damage data for 53 earthquakes. And the novelty here, as compared to the two previous work, is that they offer fatality rates related to damage state 4. Can you see my mouse? Okay, so this is the fatality loss ratio associated with the complete damage state. And then in 2016, in her book, SOAP provide judgment-based empirical fatality rates based on the data from 25 major earthquakes. And still, in her work, she emphasized the role of volume reduction on the fatality rates. And then we move on to Saul, Becker, and Spencer in their paper in 2018. They focus on the relationship between, among other topics they studied in their paper, but they stressed again the importance of establishing a relationship between fatality rates and the volume reduction of damaged building, of collapsed building. So, for example, if a soft story collapses to take place, like 10 up to 20% of the building will be reduced. But if pancake collapse take place, then all the building, I mean, about 100% will have 100% volume reduction. And in the light of very limited empirical damage data, they encourage the application of advanced 3D analysis for collapse assessment and volume reduction. And following this philosophy, Arup in 2007, Lovon et al. In 2020, Momin et al. In 2021 have applied advanced numerical modeling for estimation volume reduction, finding the extent of collapse in the for example, Arup estimated the impacted area by the debris, among other parameters, the probability of collapse. And then it is well-known Hazu's methodology for fatality estimation. They consider that fatality rates come from not only from collapse, but they offer fatality rates even for less severe damage state. But basically, the main part is fatalities that are related to collapses. And in order to estimate the probability of collapse, they establish this collapse ratio, and it is multiplication of probability of being or exceeding a complete damage state times collapse rate. And this collapse rate are basically 10%, 15%, and that means that basically not every building that is classified as unrepairable is collapsed. So the main limitation that was observed during the literature review, it is that the established metrics, fatality rates that are related to volume reduction and empirical coverage fragility function are based mainly on very limited damage data. And hence, these two parameters are the focus of my PhD dissertation. Okay, and the content of the PhD is as follows. First, we will estimate empirical collapse rates and fragility curves based on a very extensive damage data database for Italy, and then we will move to analytical methods. Then we provide analytic fragility and vulnerability function, and then we verify this fatality vulnerability function based on past event. Okay, and let's start with the empirical data. Why empirical data are so important for us? Because, I mean, we cannot model reality as well, no matter how capable we are, as the reality itself. So that is why damage data are so important for us. So in the database, we have nearly 120,000 buildings. Damage data from 6 Italian events, and the damage data are classified according to EMS 95 damage scale or damage grade. So, given the inability of common modeling platform to explicitly model collapse, so we know that when we reach 5 criteria in Opus or in other software, we have a non-conversion criteria, and we say, okay, basically this is a problem of collapse. And given the inability to model explicitly the collapse, we will estimate empirical collapse rates, so similar to collapse rate that is introduced by Hazus. So we use two mathematical formulation to model. One collapse rate is constant, so independent or invariable from intensity measure, and another mathematical form is linear collapse rate, that is a function of intensity measure, and it is and will be based on the A and B parameters. So in this sketch, you can see the panorama of the distribution of the damage state in the database. We have created a taxonomy that contains 12 building classes based on the following attributes. So that is material type, that is reinforced concrete or masonry. It's number of stories. I have created this beam, 1, 2, 3, and 4, and 5, and 6 stories together, and then seismic compliance. We classify the building as being no code, low code. I mean, this classification is established in Crowley et al. In 2021 for all buildings in Europe. And the distribution of the number of building in the database as per the masonry and concrete material as classified are presented below, and we see that, I mean, as we would anticipate, the biggest part of the buildings are of masonry. So before computing collapse rates or probability of collapse giving before, I would like you to represent to you what constitute Dama State 4 and Dama State 5 for according to EMS 98 for one-story building up and below here for RC building. So Dama State 5 is complete collapse, while Dama State 4 it is, I mean, the building is super heavily damaged. So the computation of constant collapse rate is rather trivial. It's just the number of buildings in Dama State 5 is the ratio of building Dama State 5 against the sum of building in Dama State 4 plus the number of buildings in Dama State 5. And what about the IMP parameter? In order to estimate the IMP parameter, I have created this objective function, and we select the IMP parameter such that this objective function is minimized. And basically, this is absolute difference between estimated cumulative number of DS5 building minus empirical cumulative number of DS5 building. Basically, the estimated cumulative relationship, it is adding up the probability of collapses. The empirical cumulative distribution is basically counting the buildings that are in the DS4. And IMP parameter, the best estimate, are the ones that minimize this objective function. Here I would like to introduce in red, we have the empirical cumulative number of DS5 building, while in blue we have on my left, we have the cumulative estimated number considering collapse rates as a constant, and here considering linear collapse rate. And we see that in terms of this error, establishing the error to be minimized, we see that in the case of linear collapse rate, the error is basically 3 times less as compared to the constant collapse rate. And here I show the I saw the collapse rate in both terms for one-story no-code building, one-story low-code building with 1 and 2 story, and then one-story low-code 3-4 story, one-story no-code 3-4 story. And we see that it's almost in every time, if there are enough buildings in the database, we see that there is a trend. So the higher is the intensity measure, the higher is, even though it is a slow increase, but there is a trend between probability of collapse and the increase of the intensity measure. And here I present the collapse rates and the parameter A and B of the linear collapse rate, where we see that the slope is almost in every case, apart from this low-code 3 to 4 story RC building, is negative, but in all cases it is positive. So comparison between collapse rates for Italian buildings and the one proposed by others, we see that in all cases, we see that our collapse rates are higher and sometimes 2 or 3 times more. Okay, so we get the chance to estimate empirical fragility function based on this database, and we assume that our fragility curve follow log normal distribution. Here we can see the distribution of number of buildings per each Dama state for each building in the taxonomy. And in order to estimate the parameter median and logarithmic standard deviation of the logarithmic curve, we have 3 options. We can use yes, we will use maximum likelihood method, but the first option is to use the maximum likelihood function with Bernoulli distribution, and then here it is binomial distribution, and the last case it is to use a multinomial distribution. All of these methods are well spread in the literature, but I am more in favor of using the first L function, as it is not being width dependent, whereas L2 and L1 and L2 maximum likelihood function are being width dependent, and I didn't want to was another bias in the expression. So the parameters here are 5 medians and 1 standard deviation that is constant, and are the ones that minimize this function here. We keep the logarithmic standard deviation constant to preserve the ordinal natural fragility curves, that is, the curve don't cross with each other, and the probability of exceedance a more severe Dama state is always lower than the probability of exceedance a less severe Dama state. And here we have the parameter for the 12 archetype buildings, and here are the fragility curves for the 12 archetype buildings, and we can see that in some of them the medians are very, very low. For example, here as well, here. And another factor that takes our attention is the logarithmic standard deviation, which is very high and gives this almost linear shape, a flat shape of the curves. And why it might be these, let's say, issues with our fragility of curves? We think that one reason can be under representation of undamaged building in the database. However, this does not affect the collapse rates. And it is the accuracy of the intensity measure computed based on the INGENIO shape maps. For example, for very low intensity measure like 3%, PGA of 3 or 4%, we see that there are buildings that are collapsed. So we believe that, yes, we recognize the very high variability of in the shape maps in the intensity measure. Anyway, I have to mention that this does not affect the collapse constant rates. Why? Because they are independent invariant to the intensity measure. But there is any way that we can benefit from this fragility curve? I think yes, there is a way, like excluding completely the buildings that are in Dama state 0 and computing conditional fragility curves. That means Dama state 2 or 3, fragility curve for Dama state 2, let's say, given Dama state 1, given intensity measure. So we can get conditional fragility curves, but in order to have non-conditional fragility curve, but exact fragility curve, we have to have information about the probability of exceedance of Dama state 1. So this could be done probably by numerical modeling. However, given the limitation of empirical fragility curves and the impossibility to compute volume reduction, because I don't show here because I successfully failed to compute the volume reduction of the building based in the EMS 95 and based on the ITES format, that is the Italian standard for Dama state. It does not allow you to estimate the volume reduction, because in the Italian standard of Dama state you have Dama state 4 and Dama state 5 together, so it is impossible to split that both. So, and this is why we move on to the analytical data. And we'll start with definition of RC building typology and advanced numerical modeling. And why we are shifting from empirical to analytical? First of all, is because we know exactly what is the intensity measure, because we just defined that. And the first archetype is a typical building that is RC buildings, masonry infill moment resisting frame RC building that are typical of Nepal, India, Pakistan, and it is of 3-story building, is infilled, and in order to consider the adding stories to the buildings, so we consider 2 more archetype buildings with 4 and 5-story buildings. So the main archetype is with 3-story, but in order to consider the development in the heights of the stories, we created 2 other archetypes. Another archetype is a fully symmetric RC building, infilled one, typical of Italy and Europe, and this is based on the model based on Tiziana Ruzzetto PhD thesis. And sorry, I forgot to mention here that the information here is gotten from Chaula Game et al. In 2013. What is the numerical method that we adopted? I'm going to show you what we ended up putting in my PhD thesis, but the thing is that it was a very, very long way to end up with the methodology that I am going to show you. So, to model the frame elements of beam and column element, we used beam and elastic element with 1D elastic element with concentrated nonlinear hinges in the end, and the backbone, nonlinear hinge inflection. It is the backbone code for the Hazelton et al. 2016, and here I show the cyclic response. We modeled the nonlinear behavior in shear, where the maximum capacity is computed based on the UCSD model in 2020, and this backbone curve is according to Zimos et al. In 2015, and they state that there is a point where if the shear strain hits, the column will lose its axial force capability, and so the column will not be able to be axial load anymore. And we consider this in our numerical model by imposing erosion strain level. So in the moment that the strain level will hit this target here, the element will be deleted from the model. And then we have here the backbone curve in tension and compression and the cyclic behavior. Masonry element are modeled with shell element, a fully integrated shell element, and the material property is a nonlinear concrete behavior similar to the concrete behavior relationship that I established in the Eurocode Hay. And here we have the stress strain curve in tension, and here we have in compression. In order to make sure that infills really work as such, so that they don't get extra load, but they only carry their own load. So we apply the construction stages in the model. And the ground, in order to model the ground, we use shell and solid element with elastic element that represent the ground, or that represent the ground, and I use many different modules of elasticity. In order to consider the impact of building element with each other and the interaction of building element with each other and with the ground, we imposed in the model the contact algorithm. Basically, the moment the program will recognize the interaction between each other. And finally, with this part, we used around 60 ground motion for each numerical model. They are 3D ground motion, and the selection strategy was guided by the need for the uniform distribution of the selected IMs, that are spectral acceleration, and every spectral acceleration. And I would like, before going to the result, I would like to state that the earthquake effect in the building is treated as a wave propagation problem and not as a vibration problem. So we consider the wave speed of the building. So the software is capable of doing that. So let's move to analytical fragility and vulnerability function, and we'll start by presenting to you displacement-based fragility function. And this damage model that are based on the maximum interstory drift, these damage results are estimated in the median pushover curves, because the first building is not symmetric, and they have two different backbone curves. So we will work with the median backbone curve. And in order to estimate fragility curves, we have run cloud analysis, and we will use a modified cloud approach to compute the fragility curves, where we take in account the explicit collapses and non-collapses. So let me introduce. Okay, this is a video. It's supposed to run. Okay. In any case, this is the final configuration of the building. When we see that we have lost the infills, and in the infills that are missing here, it is because they are so distorted, and we applied very high erosion criteria. Okay. So now finally is moving. So here with me, we applied the infills in the model. Okay, let's move on to a case of collapse. So we use the infills in the first story, the column in shear is down here, and then we have the collapse. Is a pancake collapse. Okay, let's move on with the selection of the intensity measure. Yes, the intensity measure is spectral acceleration, and every spectral acceleration, but in which period we are going to compute those, and for this we estimated the SRSS average standard deviation of fragility curves for various periods, and we ended up taking computing the spectral acceleration and the average spectral acceleration at the period where the spectral where the beta, geometric beta, is minimal. Okay, and we have applied the damage model in the. We show the damage model here and the fragility curve for the fifth-story local building. Another method that we use to estimate fragility curves is for damage state 1 and 2. We got the advantages of the software, and we consider that in damage state 1 and 2 will be characterized by the damage in the infills. So infills are considered damage when they are fully cracked or they are spalling, fully spalled. And we introduce here a parameter that is called damage area ratio, and is basically the number of damaged infill elements against the total number of infills elements. And in order to consider the positive and negative loading direction of the earthquake loading, we say that the total number is a union of the non-damaged element in the positive and negative direction. And here I will show a video of the number of cracks. Here's the pushover. What we see, again, we focus our attention to the median damage area ratio given maximum interstory drift, to the median curve, and we see that after a certain point, the damage area ratio doesn't change much. And we consider this ratio here as the ratio that characterizes damage model for damage state 2. And what about damage state 1? So, as we said, damage state 2 and 1, we assume that they are controlled by damage in the infill, and in order to find how much is the damage area ratio for damage state 1, we do the ratio of the loss ratio. So, loss ratio is 20% for damage state 1, damage state 2 is 5%, so the area in damage state 1 should be 25% of the damage area in DS2. And here we have these two fragility curves that are computed based on the damage infills, and here it is based on the interstory drift. And let's move on to the collapse, and the collapse fragility curves follows logic function, and is the same for volume reduction. With our modeling approach, the in case the building collapse, it would be always pancake collapse. So the probability of collapse is the same as volume reduction. In order to estimate in order to compute the fatality vulnerability function, we've adopted fatality rates from SITO 2016, catastrophic rates for the same book, given that we had always collapse, and Hazus collapse rate and vulnerability curves. Vulnerability is computed only based on the probability of collapse. We disregard the less severe damage state. And the fatality vulnerability function that we developed, we validate this in 4 past events that we have selected Emilia earthquake in 2020, Gorka in 2015, Albania, and Croatia. In our exposure model, we consider only in-field RC frame buildings that matches our archetype, the one that we created. And exposure model for the European buildings, so Emilia, Albania, and Croatia, are based on European seismic risk model, while for Gorka earthquake, it is based on the model developed under GEM framework. And ground shaking for the European building is based on the logic tree and the GMP equation produced under the European seismic risk hazard model. And here it is the number of RC building in original exposure, and here are the one that we considered. Why we consider that? Because not every building in the database matches with our archetypes, and to run the scenario fatality estimation, we use the scenario risk module of OpenQuake engine developed by GEM. Here we have a comparison between the recorded fatalities and the one that are computed by the model, and we see that the catastrophic rates are completely off in all cases. For European building, Hazus and SITO 2000 produce identical values, whereas for Gorka earthquake, it is Hazus that is doing a better job as compared to the ground, to the recorded death. And why is this the discrepancy? Okay, first of all, we believe that there is no calibration of the inter-event component on the GMPs. Truncation level was equal to 3, and according to SIVA 2016 and Fiorini 2012, this could lead to an overestimation of the losses. And another factor that I think is important is unsuitability of the vulnerability of fatality rates to characterize the considered RC building in Europe and Nepal. So the final remarks, the main outcome of the study is a comprehensive review of the current state of the practice, clear identification of existing gaps and challenges, empirical fragility function for Italian archetype building, collapse rate, identification of the limitation in damage databases, advanced numerical model for typical knockout in Nepal and local influence building typical of Italy and Europe. And we developed analytical fragility function based on drift and damage-based models. We produce fatality vulnerability function, and we verify this vulnerability function. And the future work, we tended, even during my PhD, but it was impossible with the computational power that we had at the time, to run a more advanced numerical model, because as you can see here, you can see that we were able to capture a soft story for us, but however, I would like to mention here that this is a confined one-story building and not in-field, because everything in the model is applied once, and here you see the bricks here, the columns on the ground, so this will be the focus of our work. Thank you.
Thank you, Enes. We will now have the questions by the committee. I think Antonio will lead.
Thank you. First of all, congratulations for reaching this point to you and to all of your colleagues. It's a very important achievement for every student. You have worked on a very interesting topic with an interesting work on the estimates of collapse and fatality rates, fragilities and vulnerability, which depend on so many variables. So on the hazard, on the structure, on the occupancy, and so on and so on. You have made a good overview of past efforts in the fatality modeling. And then you have used the empirical estimates and analytical and numerical estimates. So quite a number of points to make questions, and I have a long list of questions, but I will refrain my curiosity and just make a few of them. So first of all, you started working on the existing empirical data, and it's the database that you have used. It's super interesting. I give my compliments to all the contributors who have developed it before. It is a huge and a very extremely interesting work. Now, you have tried to use this empirical data, but the results that you have obtained in terms of the fragility curves, that they do not seem so realistic. Do you have any comments and suggestions on how to improve it?
Yes, I mean, we believe that one source of, probably the main source of this unrealistic behavior of the fragility curves is the lack of the gamma state zero in the database. That keeps we use the maximum likelihood method, so buildings that exceed a certain gamma state are pointed as 1, and the one that does not exceed is 0. So when we use this equation, we see it's full of 1 ball and very less below it, because it is because of the lack of the gamma state 0. And in addition, another parameter is an intensity measure, but in my opinion, this is not the most important parameter. This is the thing. But as I said during my presentation, we still can use it if we can do a hybrid approach. So use, and I believe we are good in doing, computing fragility curve for slight gamma states, so gamma state 1 and 2, and then use this empirical data to compute probability, conditional fragility curves given DS1, given IM. And then just multiplication following the Bayesian.
Okay, that could be one explanation. And that's maybe also why you have estimated collapse rates which are much higher than the ones proposed by ASUS, for instance. Okay, then you have moved into the numerical modeling. So you have a chapter on the modeling details, which is not a very elaborate one. There are many justifications that could be added to that chapter. And then you have made an interesting chapter on the analytical results, which could also use some more discussion in some of the results. One of the questions that I have on those numerical results is that you either have no damage or you have a complete collapse, right?
I either have non-collapse or collapse. Damage, of course, I do have.
You have damage, but it doesn't count towards a fatality rate. Okay. And so how can you improve this? So you in terms of collapse, you are only having a pancake type of collapse. Any ideas to improve this in the future?
The thing is that yes, this pancake collapse. In very beginning, I was before starting the thing, I was thinking that the impact with the ground will play a major role. With the current approach, I have changed the model of elasticity, the finite element type that I model the ground, and it seems that this was according to what I have now. This was not the main factor. So I've seen even experimental results in the buildings. Then when they have a pancake collapse, it is because of the shear failure. So you can see directly by eyes that the building is completely damaged without touching the ground fully. So it is not happening by the impact with the ground. At least visually, I have seen several videos of that. And now, in order to improve this, the thing is, one main problem is that I didn't want to impose any erosion criteria in the element, not at all. But the thing is that the software will not converge. For example, if the tensile strain in the masonry in Muradura goes to 100%, will not be, I mean, the time set will be very, very, very small. Because this is a wave the problem here, dynamic equation is treated as a wave propagation problem. So the dimension of the element has an importance in the time step because it's the time to travel, the sound speed. So I have several ideas to improve that. I worked with this even during my PhD, but the thing is that I tried first with solid element to model with solid element to explicitly model the rebars. I did that model without imposing any slab, without imposing any infills, and the model has 500 hours to run. So I completely disregarded it, and there are other reasons why I disregarded it. Another model that I worked was just to keep the frame as they are, slabs elastic, but infills, because I think infills have a role in avoiding the collapse, pancake collapse. But there were several issues with that approach, and one of them was the time limitation. So I will have to wait 20 hours to correct that, and this is the model I show here. I think I said that the model that I show in the end, it is a confined masonry, because even to apply construction stages with solid element in LS Dyna, it wouldn't be so easy. So, but this I think is feasible. Otherwise, for example, if you want to model a column, just a column with solid element and fields, you have to have supercomputers. So I
yes,
have this.
We know the difficulties of all this. But for instance, you have shown a case where you have no collapse. You have shown a case where you have no collapse, and and you have this removal algorithm where you eliminate, for instance, the infill elements which are collapsing, but you don't call it collapse. Right, so the building is standing, and so you don't call it collapse. But those infill failures, for instance, they can also cause fatalities. Right, so it's a bit strange that this is not considered also for the fatality count, as well as you also mentioned shear failure in columns and other types of failures which are not considered collapse. So the only real collapses that you consider is the full pancake collapse that you have in the model. Right?
I mean, this is what I ended up calling. I mean, we wanted to model a complete story loss or soft story or losing a story upstairs, but it was impossible. So we considered structural collapses. We did not consider the effect in the infills, even though this is an important parameter, and But no, here we focus on the volume reduction of the building.
Okay, thank you. And then in the end, you have a chapter with the validation with specific past seismic events, which is a difficult issue, another difficult issue to deal with. So with several ongoing efforts and still no established methodology to do it right, and you have all the uncertainties in the distribution of the fatalities on the building typologies, occupancy, and so on. So in your study, so I don't know if you have looked into other possible methodologies that could be used for this comparison with empirical data, or not?
Please, could you rephrase the sentence because I couldn't?
Yes. So in the final chapter, you have the validation with empirical test results. Did you look into other possible methodologies to make this comparison of fatality rates with empirical data? Because the results that you get, so in 3 of the events there are no fatalities, and you have a large number of fatalities, and in the events where there are a significant number of fatalities, you also have an even larger, much larger number of fatalities. So, have you looked into other possible approaches to deal with this?
No, I mean we didn't do that. I mean, we just run scenarios, simple scenario with a fatality vulnerability function and with the exposure model that was developed by other institutions. The only thing that we changed, it was picking up the models that we thought would match closely with our models, and I mean, other than that, we haven't seen other stuff.
Okay, thank you. I'm satisfied. I don't know if you have any other question.
Yes.
I have more than a question, a suggestion. Firstly, why you make this choice to use less data?
Because of the explicit solver to be able to run.
Yes, but no, because I said this because it complicates a lot. You need to take into account for a better analytical model the influence between shear and flexure, for example. When the shear acts really on your building before the flexure, or it is the contrary, it depends on the characteristic of the building. So the influence of the normal forces in columns together with flexure. So there are a lot of things that need to be calibrated before to make a better comparison with the existing damage state you have analyzed very carefully. Okay, so I suggest you to move to another platform to make easier your analysis.
Okay, let me tell you something because I forgot to answer to the first Dr. Antonio, sorry. In the middle of the PhD, I was about to change the software. I wanted to use extreme loading software. So it is based on the applied element method. I believe you are familiar with applied element method. So I spent time on that. Fortunately, I didn't buy the software because I was about to pay by my pocket to get the software. Because my supervisor decided that it's too late to move, only because of that pancake collapse. Because I thought it is not feasible that in any case we're getting, in case it is collapsed, there is 100% volume reduction. But there is a guy in the Michigan University, Omar is his name, and he did a similar exercise with infield RC buildings, even good RC buildings. So probably they were even designed according to very advanced seismic code, and in all cases you were getting pancake collapse. In all cases. So God help me in this case not to change the software.
Thanks.
Thank you.
Is there any question from the audience? Okay, apparently not. So thank you once again, Enes.
Thank you.